Hello students. So we are almost at the fag end of module 1. This is most likely the last lecture, and in this lecture I'm going to touch upon multiple topics, small topics, to give an what we can say is to round off many things that we have touched upon in this module. Okay, so to begin with, what we have seen was the stack pointer. Along with that, we have a couple of other pointers that RISC-V provides us. Let's look at them. The very first one is frame pointer. So as you are aware, when we start uh, uh, executing a procedure, it many a times we might need to place lot of temporary variables or the local variables right onto the stack to basically to free up the registers. The classic example for register spilling. So all these variables will be placed onto the stack, and we saw that we can retrieve them using the stack pointer. Now, it if we look at the procedures stack, it will tell us what is the activation record of that procedure. Basically, how many bytes have been consumed by this procedure, what is the starting address and the ending address meaning the stack pointer itself, right? So this together is called activation record, and the frame pointer points to the first location of this activation record, meaning the frame pointer would be having the address of the very first variable that we have placed onto the stack for this particular procedure, right? Just like we keep growing, placing the elements onto the stack and retrieving them, the stack pointer can change during the execution of this procedure, but the frame pointer will always point to the first location uh, of the frame. So many a times it is easy for us, the persons who are programming at the assembly level, to use the stack pointer rather than the sorry to use the frame pointer rather than the stack pointer, because the stack pointer can change midway. So for this convenience, the frame pointer has been provided. Now the usage of the frame pointer is not mandatory, and typically the for the programs that we write, we don't need to use the frame pointer as such. So if we want to understand how it would typically look like, let's say here we have the caller. The caller's activation record is something like this. The caller's frame pointer is here and stack pointer is here. So when we look at this, we would say that the caller function or the caller procedure has used up so much of space on the stack. Now, when there was a call to a procedure, the callee, we have placed a lot of data onto the stack here, right? And when this particular procedure is getting executed, the stack pointer can uh, grow further down or shrink up, but the frame pointer will always be pointing to the first location here. So if we want to, for example, let's say we have placed registers x5, x6, x7, x8 and x9 onto the stack. Let's say x5 is the first one we have placed. Following that we have x6, x7, x8, x9. Now the stack pointer will be pointing to x9, but the frame pointer and the frame pointer will be pointing to x5. Now midway, somewhere during the in the execution of the procedure, based on logic, we had to remove x9, right? Then the stack pointer would be pointing to x8, and if we want to retrieve x5, for example, we can directly use the frame pointer instead of using stack pointer and subtracting some locations as an offset. That is the convenience provided by the frame pointer. Now at the end of the program execution, because we free up all the stack usage, uh, or we zero out the stack usage of the procedure, when we come back to the caller procedure, the stack pointer and frame pointer will be restored. So in Venus, this frame pointer is not supported, though it is labeled. It will not will not be able to use it much efficiently, right? Just like stack pointer, we have to keep track of it ourselves. So along with the frame pointer, there is one other pointer that is given to us, which is global pointer. But before that, a small uh, definition of two terms: the automatic variables and static variables in C. The static variables are those which are preserved across procedures, and these are defined typically with word static. And the an easy to correlate example is global variables that we have in the program. On the other hand, we have automatic variables in C, which are typically used, declared and used within a procedure, and they will not be accessible once we exit that program. So as you might guess, these would be the local variables of various functions, etc. Right now, how do we identify the locations of these global variables? Is using the global pointer, GP. It's uh, X3 register is the one which is having the global pointer. I think I missed the frame pointer. Will be available in X8. Now, using the X3, we can access all the global variables that we have declared in this particular program. Now, a quick check that you can do is when you open Venus this time, see the value of X3. It would be 1 triple zero and followed by 0 triple zero, right? This location is the first location of the data segment or the data memory, right? The X3 will always be initialized to this particular location. It means that whatever we uh, place in the data segment will be uh, stored in the memory location starting with this. So, and all these variables that we have defined in .data can be accessed using the global pointer. Instead of remembering this particular location, we can use X3 and retrieve them. So with this, a quick snapshot of overall memory, how it looks with respect to the program. So the very first, there will be few locations that will be reserved for the OS or the kernel. Following that, we have the text segment for the machine code of the program. It means that this is where all the instructions of this program are available. Following that, okay, so when we place, so all the instructions we place below the dot text assembler directive in Venus, right? So they will be placed in this text segment. Following that, we have the static data segment for the constants and other static variables, like I've just mentioned in the before slide, and they will be placed in the static data if mentioned and below dot data in Venus. So this would be the data segment. Following that, for handling all the dynamic memory location allocation, we have what's called as heap, right? So you can imagine that heap is available here in the dynamic data segment. So typically, if you want to allocate memory using a malloc or new, or if you want to free up such spaces you are already allocated, you would use free functions, right? All those would be operating on the data in the dynamic data range or dynamic data segment. In C, the allocation and deallocation of all the dynamic data needs to be done by the programmer ourselves. But in Java, it's a little sophisticated and it will be done automatically. But the takeaway, at least for this module, because we'll be primarily dealing with C kind of examples, the working would be uh, the working needs to be handled by us. For example, if you want to create a node on linked list, you need to allot pick the dynamic data segment and allocate the space, fill it up with the required data, and have a pointer with you. With that, a discussion on whether we had to use pointers or arrays. So to understand that, we'll pick an example which is clearing the elements of an array. Means all the elements of that array are initialized to 0 or reset to 0, for example. And let's say this array is an array of double words. So here is one small procedure or function that does this. We pass the array and we pass the size of the array, and within the function what we do is we loop, and we for each we pick the each element and assign 0 to it. So here this is the pass by value example, and let's say we can achieve the same thing with pass by reference, where we are passing the pointer to the array and we are still passing the size of this array. So what happens here is, again, we are still looping, but here we are the iterator variable is the pointer, or the address of this array will be the starting location of this array is stored in is initialized to p. Sorry, p is initialized with the starting address of the array, and we increment p till we head the till we go to the last element on the till we go to the address of the last element of this array, and we use this pointer and initialize to 0. So this is passed by reference and this is passed by value. Now let's look at how the assembly code of both would look like. Let's assume that the starting address of the array is available in x10, size is available in x11, and I is available in x5. And here p is available in x5. Just for simplicity, I have used the same registers. So here this is how the program would look like when we are doing the pass by value, um, when we adopt pass by value concept, right? So we are initializing the value of I to 0 here, x5, and following that we are shifting the value of I, the value in I by 3 positions, and placing it in x6. X6 is the temporary register here. Basically we are doing this to get the offset uh, of the element, ith element of the array, because it's an array of double words. If it was simply words, then we would have placed 2 here. Now once we have the offset, so we because we already have the address of the starting location, we add this offset and generate the address of ith element of the array, and it is placed in x7 here. Now in that location we are writing 0. So we are storing 0, sd x0 0 x7. So what this does is, in the location given by x7 plus 0, which is the address of ith element of array, we are storing the value of 0. Following that, we increment the value of I. This is a simple add I instruction, and this incremented value of I will be compared with the size of the array. As long as we are less than the size, we are going to loop back. So a simple straightforward for loop implementation. Now let's look at how the assembly code would look like when we are dealing with a pass by reference. So here the very first instruction is that we are taking a copy of the first element of the array in x5, which is the p here, and we are placing 0 into that. So it's similar to the instruction here, sd x0 0 x5. Following that, we are incrementing the value in x5 by 8 positions. Why is that? Because it's an array of double words, each element will take 8 bytes, and because memory is byte addressable, the elements in this particular array will be 8 spaces apart. So the value in p, the value of p is incremented by 8, and the to know what is the address of the last element of the array, we are going to so if we imagine that the last element of the array is the null character, then that's why we have placed that it should not reach till then. We should stop with the element that is just before that, right? So but either way, we need to get the address of this last uh, element of the array, here the null character. So using because the size is available in x11, so we multiply it by 8, and that value is stored in x6, and x10 is the starting address of the array. So to that we add the offset of the last element of the array, which is in x6, and that's when we get the address of the last element of the array. Now we have the address of pth element, and then we have address of the last element, and we compare them, and as long as the address of the current element, which is here I and here it is the p, is less than the last address, we are going to loop back. Now here you find a use case where we can to distinguish where we need to use BLT and BLTU, because here we are dealing with addresses. We are pretty much sure that they will not be negative, and typically the address space of memory is too huge, so we need not waste space in the register saying that it's a signed value. We can say that it's unsigned value, so we'll get higher range, and we can compare the values of them as unsigned numbers. On the other hand, we are comparing the value of I and the size of the array, and if not the size, at least the value of I can still be going to negative if not handled properly. So that's why we are using the signed version of BLT. Now if you look at the dynamic execution count of both these programs, right? So let's say we have um, 10 elements in this array. So let's see how many instructions will get executed to initialize all the 10 elements of this array to 0. We execute the first instruction once, then for I equals to 0, SLLI, ADD, SD, ADDI, and BLT will be executed once. So for I equal to 1, they will be executed again, so on and so forth. So the dynamic instruction count can be 1 plus 5 times the number of elements we have in the array. So if we have 10 elements, then it would be 50, and overall instruction count, dynamic instruction count, would be 51. Now let's see what happens here. Sorry. Here too, the first instruction will be executed only once, and for each element of the array, SD, ADDI, SLLI, ADD, BLTU will be executed once each. So the dynamic instruction count will look similar to that of the pass by value. In both cases, we have to execute 51 instructions for an array of 10 elements. Now the question is, can we do any better, or can the compiler do any better when it is generating the machine code? So at the high level language, right, we are either writing the pass by value and pass by reference. Now if it is pass by reference, then we are we can provide some additional advantage or additional exposure to the compiler, and it can generate an optimized code which can look something like this. So again, the first instruction is similar to the previous one, where we are getting the element of the first where we are getting the address of the first element of the array in X5. Following that, we would need to generate the address of the last element of the array only once, and we can reuse it multiple times. So the compiler can identify this redundant operations that are happening, and it can move the SLLI and add instructions out of the loop. So earlier they were part of the loop, now they have been brought out, right? So the address of the last element of the array is calculated only once and reused multiple times. Once it's calculated, what we are doing is we are assigning 0 to the element uh, which is pointed by p, and we are incrementing p, and this incremented value of p is compared with the generated address in X7, and we are going to loop back only to uh, SD instruction. So here the dynamic instruction count would be the first 3 instructions will be executed once. Following that, the remaining 3 instructions will be executed once for every element of an array. So if we have 10 elements, earlier we took 51 instructions to execute it. Now we would, earlier we would have executed 51 instructions, but in this case, if the code is optimized, then we just need 33 instructions. So the lesser the instructions, the faster the program would run. So that's what our uh, execution time equation says, right? The instruction count. If the lower it is, the better. So even though when we are dealing with pointers, right, the code might look not so obvious, or implementing a logic using pointers might be a little tricky. But if when we do that, the compiler can you can imagine that the compiler is getting more freedom to optimize the code. So make it a practice to visualize and write the code using pointers. Okay, with that, let's move on to the next small topic, which is how to handle the heterogeneous data structures in at the assembly. Now we have seen is array. Now let's see if we want to handle or realize a structure at the assembly. The implementation of structure is very similar to that of an array. What happens is all the components of the structure are stored in contiguous memory locations. Contiguous meaning side by side, right? Now how do we access this structure is there will be a pointer to this structure, pointed to the first byte of this structure. Now, let's say we have a structure REC, short for record, and it has 4 elements in int I, int j, int there is an array A of 3 elements, and there we have a pointer. Right? If we try to visualize how these would be stored in the memory, it would look something like this. So this is the offset. Offset 0 would let's imagine that there is a pointer to the first location. So with that, if we add the offset 0, and if we use that address to load a value, that would be the value of I. And if the offset is 4, we could access the element j. In the same way, we after an offset of 8 from the starting of the structure, we can access the element a of 0. Again, plus 4, which would be 12, we can access a of 1. Plus 4, which is 16, we can access a of 2. And if the offset is 20, then we can access the um, pointer p. Just like we were trying to move from one element of an array to another element, here the offsets need to be noted, and if we give the proper offset, then we can we can access the correct element. Now, if we think about it, who will be generating the offsets, and that is the job of the compiler. So again, during the compilation process, it will analyze the individual space that each of these elements would take and accordingly generate the offsets and use these offsets in part of the machine code, so that we when we are loading and storing these elements, appropriate or correct offsets will be used. Okay. Now, it is very important to note that the machine code, when you look at the machine code, as you already understood, it is just a sequence of zeros and ones, right? It does not contain any information about the field, or the field declaration or names of the fields. It would be just a sequence of loads and stores. For example, let me go to the previous slide. So in the assembly code, let's say the starting address of this structure is in x10, and if we want to load a0, what we would write is load, let's say we want to load it in x11, load ld x11 comma 8 and in brackets x10. So what we are saying is the value in x10, which is the starting address of the structure, will be added with an offset of 8, and the memory will supply whatever value is there in that particular address and write it into x11. Now if you want to access p, let's say, it would look something like this: ld x11 20 in brackets x10, right? Now when we look at both the instructions, we will not be able to figure out whether we will not be able to make uh, an insight that, okay, if the offset is 8, it is an array element; if the offset is 20, it is a pointer, right? That kind of information will not be available in the assembly. All it has is a simple load and store. So it's you can see the amount of heavy lifting that is being done by the compiler, because at the hardware we will not be able to distinguish whether it is a an integer or pointer to an integer, or it's an array or anything as such. At the hardware, all we do is deal with individual values one at a time. So it is the duty of the compiler to generate the appropriate offsets and accordingly generate the required load and store instructions. Okay, with that, let's look at, I think, the last topic of this module, which is addressing modes. I have already touched upon this uh, almost 3-4 lectures back when we were talking about the register operands, immediate operands, and memory operands. So here is a quick refresher of that. Basically, the addressing modes that are specified or indicated by the ISA give us an information on how an operation is specified in an instruction, whether the operand is available in a register, or whether it's available within the instruction, or whether the operand is available in memory location, etc. So basically, addressing mode dictates how to get the address of an operand. So for the various the addressing modes that are supported by an ISA obviously will be determined by the ISA itself. And uh, if we have multiple such addressing modes, it will be able to help us with handling complex data structures and referring individual elements in those data structures. But if we have multiple addressing modes available, then you can imagine that at the hardware, to regenerate the address, it needs a little more effort. So again, the discussion on RISC versus CISC would come. So in typical RISC ISAs, there will be very, very few addressing modes when compared when we go to the CISC style ISA, there will be many addressing modes. So I'll give you example of both. We already seen the RISC ISA, but here is the quick summary. In RISC, we have only 4 addressing modes, right? It is immediate addressing, register addressing, base addressing, and PC relative addressing. So in the immediate addressing, what happens is the value of one of the operands is readily available in the instruction itself, right? So here there is no concept of address of that particular operand, but rather the value of the operand is readily available. And here you would already you can already correlate that many of the uh, immediate instructions, ADDI for example, fall into this category. Now when we look at the register addressing, it has 2 register operands as source and 1 register operand as destination. So what it means is the value of the values or the operands 1 and 2 can be brought from the registers RS1 and RS2. So what this instruction indicates is go and access the registers RS1 and RS2 from the register file. Okay, whatever the values are, perform the operation, and the generated value is returned back to the destination register. The same thing here. So here in the register addressing, the address of an operand is actually the address of the register. If we have 32 registers, RS1 and RS2 will be 5-bit values specifying which particular register has that operand. So an example of register addressing would be the add instruction itself. Add x1, x2, x3 for example. So x2, x3 are the source operands and x1 is the destination operand. We have you would have already seen this multiple times as part of the assignments itself, right? Following that, what we have is the base addressing, right, where the instruction, I'm sorry, okay, so the instruction has an immediate value just like the immediate addressing, but what we expect is the value in this in the immediate field is added to the value in RS1. Okay, that would be here, and whatever that address, whatever the result is, we interpret that as an address to the memory. We go to the memory and get go to that particular location, and we get the address and place it, we get the value and place it in RD. So for example, here you can imagine uh, a load instruction. That's what my example was. We can place the value from the memory to the into the RD, or it can be a store instruction where the value in RD will be returned to the location which is given by immediate field plus the value in RS1. So the load stores typically belong to base addressing. Following that, the fourth and final addressing mode that is given by RISC-V is PC relative addressing. Now here is something interesting where we have the immediate field, we have RS1 and RS2, but what we expect is the value in this immediate field is added with PC, which is the program counter, and that will give us the location to access in the memory. So now what to do after that is again depends on the instruction, right? So we can say here that the value of PC is being used. Now you can imagine that AUI PC can come into this category where the value of PC is used, right, and the value of the immediate field is used together, they are added, and uh, the something further will be done based on the instruction itself, right? So these are the 4 addressing modes in RISC-V. Now if we want to quickly look at how the addressing modes would be in a typical CISC style ISA, I'm picking the IA32 ISA, which is short for Intel architecture, x86 architecture, which is 32 bits. Now here is a list of various addressing modes that are available there. So earlier we had only 4 in RISC-V, but we have many here. To quickly correlate, so the very first entry in the table you can see is immediate. This is very similar to what we have seen in the RISC-V. Following that, we have the register addressing, again very similar to what we saw in RISC-V. Then here we have a new addressing mode, which is memory, where the value in the immediate field will be used to directly access that particular location in the memory. This is not available in RISC-V. We always add the value in immediate field to a register or PC, and then alone we are going to access the memory. But in CISC, specifically IA32, we can directly access the memory using the immediate field itself. Following that, we have the indirect addressing, or again this would be the base addressing. Oh, sorry, base plus displacement is here. So here we have an indirect addressing where the location to be accessed in memory is given by the value in register, and the register name here is EA. Right, so we access the register, whatever value is there in the register, that will be interpreted as an address, and we go to the memory location and access that address, either for reading or writing. And then we have the base plus displacement or offset, we can say. This is similar to what we see in the base addressing mode of RISC-V, where the value in immediate field is added to the value in register that will give us the location to be accessed in the memory. And there are many other different addressing modes that will help us to generate the address in a much more uh, as you can see, we need to do additional computations to generate the address, right? And these computations again need to be performed at the hardware using an adder or subtractor or multiplier, whatever, right? So it's important to understand that these computations themselves are not what we expect. These computations we are doing are only to get the data. Now we need to do the actual computation on that particular data. For example, when we want to do matrix multiplication, right, all we are all we are concerned rather would be to multiply the value and to pick the correct uh, element of aij, and multiply it with another correct element jk, for example, right, and that will be assigned to an element cik. Now all this computation, whatever we are doing as part of addressing mode, is to generate the exact address of aij, bjk, and cik. They are not actually performing aij times bjk, right? It is very important to understand that. Here all the addressing modes help us to generate the address of the element or the data that we want to perform operations on. Now uh, to support many complex addressing modes, we need to have complex hardware. That's why uh, these are supported only in CISC style ISA, where we can afford a complex hardware. But in RISC style, we want to keep the hardware as simple, as much simple as possible. So we have limited set of addressing modes. Following that, a quick summary about the instruction encoding. Again, I have touched on this at multiple times. Whenever a new instruction is introduced to you, I have already shared the instruction encoding of it. Basically, it will help us on, or it will help the assembler to convert an assembly code into a machine code, right? So that's why we split I assume a 32-bit space, and we split the 32-bit space into multiple fields, and each field will be uh, the position of each field is very well defined, and the purpose of each field is also very well defined. So the assembler will encode the instructions following the instruction encoding again specified by that particular ISA, right? So what we have seen in RISC-V is we have R type instructions, means R type encoding, I type, S type, SB, UJ, and U type. Just these 6 type of instruction encodings are there. Now, if you are curious, just look at the IA32 architecture. You'll the instruction encoding is not limited to 6, but there are many other different encodings that they do. Now again, whenever we are trying to decode this particular machine instruction, which is basically a 32-bit sequence of zeros and ones, trying to figure out which instruction it is, right? That's part of the instruction decode. We are going to dwell into this particular aspect in module 2 anyways, but here I would like to give a couple of quick points. Just like the computation we do for generating an address of an data as part of addressing mode, right? Here, whenever we are trying to decode and identify the instruction, means whether it is add or add a or subtract or multiply, left shift, right shift, etc., we need to provide the required hardware. And if we have many different instruction encodings, obviously the hardware will become complex. So accordingly, for any CISC style ISA, the instruction encoding will be limited to very few types. But when we go to CISC style ISA, the instruction encoding can be much more diverse, right? So what the assembler does specifically for RISC-V is, for example, let's say add x1, x2, x3 was given. So it will first identify that it is an add instruction based on the mnemonic ADD, and it will go to the assume that there is a small lookup table which has the opcode, function 3, function 7 of the add, right? It will take those values, and based on the instruction itself, which is x1, x2, x3 here, x1 will be the destination register, so RD will be replaced by 5-bit value of 00001, right? And RS1 will be x2, let's say it will be 00010, and RS2, let's say, is x3. Then the assembler will replace this field by 00011. Now, because it has the opcode, function 3, function 7, RD, RS1, RS2 values, the machine code will be a sequence of 32 bits with these appropriate fields that will be written in the binary, right? So the end binary that you have is the machine code of an add instruction. So this instruction encoding that is given by the ISA will be used by the assembler to generate the final machine code. That is one half of the story. Now, what is the other half is, at the hardware, all we have is a sequence of 32 bits. Now, how do we figure out that it is actually add x1, x2, x3? We are going to look at the LSB 7 bits followed by function 3 bits and function 7 bits at the hardware. When we look at these three fields, we are going to figure out that yes, it is an add instruction. Again, following the same ISA, right? After that, we are going to pick the bit positions which will be giving us RS1, bit positions which will be giving RS2, bit positions that we will be giving RD, right? Now, because we know the register numbers, here x2, here x3, right? At the hardware, now we go to the register file, pick the value which is there in x2, pick the value which is there in x3, and because opcode function 3, function 7 will tell us we need to add these two values, there the ALU will perform the addition, right? Whatever the resultant is will be placed in the value of x1 that will be given by the RD, right? That's how we are going to execute this particular machine code at the hardware. So this specific task we are going to dive in much deeper in module 2. In module 1 we are going to we stop at a point where we convert the add x1 x2 x3 into a sequence of 32 bits of zeros and ones using the instruction encoding given by the ISA itself. So I have touched upon this point already. How does the hardware identify and execute? This would be a very interesting task in module 1, and we have a lot of different aspects to touch upon, right? With that, we are almost at the end of the lecture. Whatever RISC-V that we followed was the base architecture, right? And there are many extensions that have been provided to RISC-V. And remember, it's an open ISA. So if you feel some particular instruction is missing, you can also propose to add and add as an extension to this basic RISC-V ISA, right? So here we have the instruction counts in each of these uh, extensions. The base architecture has 51. To that, the RISC-V M extension has 13 additional instructions which are specifically for multiply and divide instructions. And then we have RISC-V A extension which is dealing with atomic operations and so on for floating point and compressed instructions. We have limited only ourselves only to the base architecture. So if that's the reason I have clearly specified in one of this lab tasks of lab 3 that restrict yourself to integers and forget about any decimals or anything like that. Okay. So with that, we conclude the module 1. And today I have touched upon various small topics. They are spread across sections 2.13 and 2.14. And if you want to get an overall view on how the any particular high level program, let's say a C program, will be eventually converted into an machine code, means the role of compiler and the role of assembler in a more descriptive manner is given in uh, section 2.12, right? It's a very detailed write up. I would strongly suggest you all to go through it, right? I have touched upon various steps in many of the previous lectures, right? The sections 2.9, 2.11, 2.15 through 2.19 are optional. I will leave it to you. In case you are interested, go through them, and if you have any doubts, post a question. We'll get back to you. With that, I'll conclude module 1. Thank you.